will current flow? It's going to be clockwise or counterclockwise?
Clockwise.
Why?
Because it's going from the negative plate to the positive plate.
Current's going from the negative plate to positive plate?
Well, it doesn't go between them, but it goes in that direction. No, current goes in the opposite direction of electron movement. It's going to go counterclockwise.
So you're going counterclockwise now?
Yes.
Because, wait, so you have electrons here.
Yeah.
Which way will electrons go when I complete the connection? So electrons will be going this way. So which way is current flowing? Clockwise, you were right the first time.
Okay.
So my current's going to be flowing this way. So I'm starting here. If I do my voltage loop here, I got a voltage going across here. So my voltage loop will start here. I go around clockwise. I'm going to gain voltage going across the capacitor. I have to lose voltage going across the inductor. I guess technically until I stick in the more specific information. Plus, the sum of all the voltages is 0. Obviously, this is going to end up being a negative number. Across the capacitor, it is the charge divided by the capacitance. Minus L delta I over delta T. Make sure I get my signs correct here. Yep, okay. Equals 0. What is current? Let's flash back to the beginning of chapter 21 or 20. Chapter 20. What is current?
Changing charge right? Changing charge every change time?
Yeah. But recognize that the charge that's going across through the inductor is the charge that has already left the capacitor. That's the charge of the capacitor. This is the charge going across the inductor. This charge that's causing this current is not this charge. They are different charges. Because we start out with all this charge on the plates, and the charge that's going across the inductor is the stuff that's left the plate. This is the charge on the plate. This is from the charges leaving the plate. So there's an extra minus sign that pops in there. So if I look at let's see, how do I want to do that? I'm hand waving this anyway. All right. So Q plus L delta I over delta, throw in a delta Q over delta T. Delta T. So we now have this equation here with charge in it. C is a constant, L is a constant, well, time varies, and Q varies. So Q over C is equal to the negative L of the change, generally written. Now for those who have calculus, this form might look a little bit familiar. If you have not had calculus, you might go, oh, okay, sure, whatever. Well, what I'm looking for is a function of charge that when I do the change of the change, I end up basically with something related to charge. I need some function whose, well, don't forget when I'm doing delta Q over delta T, if I have some function of Q here, if that's Q versus time, then delta Q over delta time, it's just the slope. This is some positive value getting smaller, then it negative for a little bit, then it's positive again. And if I do the delta squared Q over delta T squared, what I'm doing is doing the slope of the slope. So it starts out as somewhat negative there, and then 0 at that point. That is badly done. crudely like that. So I need some function that when I do the slope with a slope, I have something that looks kind of like what I started with. Well, actually, it's negative, so I want the flip of it. And what function, when I do the slope with the slope, looks kind of like what I started with, except the flip?
A straight line.
No.
Well, if it's zero, if that straight line is zero, then yes, the slope is zero and the slope is zero. So, well, except it's flipped upside down. You take that and you rotate the line.
Darn.
What non-zero function?
Is it a trigonometric function?
It is a trigonometric function.
Is it sine?
Or,
Cosine?
yes, it's one of those two. Whichever one you pick. If we start with cosine, so if that's my cosine curve right there, my sine, it starts out 0. It's 0 here, it's 0 here. My slope becomes negative, then it comes back to there. So if this is cosine, this is actually negative sine. And if I do the slope of that, I start out at 0 here, and I have 0 here. My slope is negative, goes to 0. That's negative cosine. So what are the implications here? As current starts flowing through here, the inductor is going to create this back current, which is going to slow the change, which attempts to slow the change. But since I have a trig function that's oscillating back and forth, what's going to happen is, if the inductor were not there, all the charge would immediately go over to the, all the electrons immediately go to the positive plate, neutralizing the whole thing. You basically have discharged the entire capacitor. With the inductor there, all the charges are going to basically come over to this side, and then they're going to oscillate back, and then they're going to oscillate this way, and then oscillate back. And in an ideal situation with absolutely no resistance, it will go on forever. Realistically, yeah, there's resistance in the wire. So that doesn't actually happen. And then one other fun thing is, there was questions on this before I talk about the last little change we need to make to Maxwell's equations. All right, so recapping Maxwell's equations. We have the change in the electric flux through any closed surface is equal to the enclosed charge over epsilon sub 0. The change, or not, the sum of the magnetic flux through a closed surface is equal to 0. We have Ampere's law now. These are Gauss's laws, or Gauss law, laws of electricity and magnetism, respectively. Then, if I do B dot L, that's going to be equal to mu naught I. This is Ampere's law. And then E dot L, in other words, the EMF, is equal to negative delta phi B over delta T. And this is generally called Faraday's law, although I think Lentz deserves credit, so Faraday and Lentz's law. At the heart of it is Coulomb's law and the Biot-Savart law. Everything else is math and definitions. But there is a small flaw here, and this gets pointed out by Maxwell. We had Kirchhoff's rules that if I do a loop around if I do any loop around a circuit, my voltage gains equals my voltage losses. In other words, the total voltage is zero from any point n itself. And then we have the junction rule. Current flows in equals the current flowing out. So let's go to our lovely capacitor. We have charges flowing onto a plate and then charges flowing off the other plate, but what about in between? Sort of expanding that. So as electrons show up here, I have electrons leaving the other side. But if these rules are true, it should also work if that's my Gaussian surface right there. I have just take some sort of three-dimensional surface around a single plate. I have charges flowing onto it, but I have nothing flowing off of it. Try to do this in the right order. Apparently not there. Yeah. All right. So we need to resolve that. Apparently that's the cliffhanger right there.